Want to build the world's best mechanisms that will never jam? These easy tips and tricks will make your designs much better and make sure that they will never jam.
Most people don't realize it, but in our everyday life, we are surrounded by
interfaces with the sliders. And when they fail, it sucks. Perhaps you have seen our video about creating the world's best keyboard, the Seneca. One of the elements to master in there is guide ratio. So when you have a keyboard with a space bar, there's a switch inside and you don't want that to jam. So that's why you got these small metal bracket that is called stabilizers. Let's have a look at another example, a small test 3D printed rig that we have made. There's a small slider here, and what we want to avoid is when we apply force. Now you can see I cannot almost get this up, and that's due to what we call the guide ratio. So if I take this orange slider and replace it with one with greater height, see it here, then this one moves much better without jamming. Why is that, and when is the critical point for when it starts to jam or not? Let's explore.
Let's take a look at the CAD model in RD8 and make a section cut. It looks something like this. If we take a look at the physics behind it, then we'll have an input force, which will act as a lever arm. We'll have some reaction forces, and hence we will have friction. We can then solve these equations for the total friction force, and we get this expression. We can now take and copy paste this expression into RD8. We can then write in the equation into the calculation formula field. In the calculation section, you can see that we have created 4 parameters, A, B. The input force is set to 10 newtons and a friction coefficient of 0.2. This results in a friction force of 16 newtons, which is greater than the input force of 10. So this is what causes the mechanism to jam.
How to interpret sensitivity. Let's take a look at an example. So in this case, the friction coefficient has a sensitivity of 80. What does that mean? The sensitivity describes the gradient or the slope of the parameter in the equation. By changing the value, an absolute amount of 0.1 impacts the end result by a factor of 80. So a little change of friction coefficient means a huge difference in the friction force. So let's try to change the number here from 0.2 to 0.1. And we see that the nominal value changes from 16 to 8 newtons. So how do we make a better design that is not that sensitive? Let's try to change the nominal value, the slider height B, from 5 to 20. We see a big change in sensitivity. It drops from 80 to 20. And we can make a Monte Carlo simulation of this. Let's compare the results. So you will see in the first result, or the original result, will have a variation of approximately plus minus 8 newtons. And in the updated design with a lower sensitivity, you will only have around plus minus 2. So a much lower variation. In cases where you're having unlinear expressions or very sensitive parameters, it's a good idea to switch from worst case studies to Monte Carlo. Being able to articulate and describe and understand a concept by math and physics is paramount in my opinion. That's really what makes the difference between a good engineer and a great engineer. So how can you remember this, and what should you remember going forward? So let's make a little trick here and make the friction force equal to the input force. So if we do that, then we can rewrite the equation and solve for the friction, and we get this expression. We can put it up a little nicer here, something like this. The relationship between B and A should always be greater than the friction coefficient. So I will go into RD8 now And I have pre-cooked an example here with the equation we just explored. And I put that into the calculation formula field. And actually the only two parameters we need to balance is the distance A and distance B. And if we see here, the critical point for this equation is that the result is 0.1 when we have this ratio. So we need a friction coefficient that is lower than 0.1 for this one always to work smoothly. So what happens if we change the value from 5 millimeters to, let's say, 20? You see that the result changes to 0.5. You should interpret this, and then you can allow up to 0.5 as a friction coefficient. So the really important thing to remember here is the relationship between A and B. If you look at the equation here, you see that the greater that we make B, the more robust this design will be. So always strive to minimize A and maximize B to get the best sliding capabilities possible. Hope that these tricks and rules of thumb were useful, and hope that you will never do a design that jams again. Peace.